Hello again, this is part 7 of the lecture Monolithic versus Layered. This is part 7. We're going to talk about preparation guidelines, which is very important for dentists and dental lab technicians to know and run a comparison between layered and monolithic prostheses and amongst monolithic itself, for monolithic zirconia or monolithic lithium disilicate, what to use and how and what's the indications. So under preparation guidelines, I would like to show this example. It's very important examples from Spear Education. This example shows that the first molar is prepared for a full contour monolithic Emax crown. We established that we don't want to say Emax, we say lithium disilicate, but that's the way they published it. So lithium disilicate. So number 6 here, or first molar, is prepared as a monolithic lithium disilicate, while the second molar is prepared for a full contour monolithic zircon crown. So monolithic lithium disilicate, monolithic crown. Okay? Now I'm gonna real quick click on all of them and just give you the end result as to speak. See, 1.5 to 2 millimeter cusp or tip occlusal reduction, 1 millimeter circumferential shoulder reduction or wall thickness 1 millimeter, 1.5 millimeter occlusal reduction of the functional tip. Now this is for the lithium disilicate. Okay. Now for the zirconia, you're talking about 1 to 1.5 occlusal depth. All right, 1 to 1.5 cusp tip occlusal reduction, and then 0.5 millimeter gingival chamfer reduction, 1 millimeter occlusal reduction of the functional cusps. In other words, if you want to sum this up, if you want to sum it up, for the lithium disilicate, you would say that you're talking about average of 1.5 millimeter thickness. All right. The only thing that can go less than 1.5 millimeter thickness is 1 millimeter for wall thickness when it comes to lithium disilicate. So you're talking about 1 to 1.5 millimeter of thickness for lithium disilicates in the back. Number 6, first molar. While when you go to zirconia, you're talking about less than that. You're talking about 1 millimeter, almost average of everything, and then you're talking about 0.5 millimeters by the gingival margin. Okay, if it's a chamfer reduction. All right, 0.5 millimeters. So you're talking about 1 millimeter zirconia almost, and then 1.5 millimeter lithium disilicate almost all around. All right. Now the reason I put this up, this is a scientific publication, and I want you to compare it to, we're gonna take preparation guidelines from different companies and compare it to this. Of course, companies would tell you that you can go with less wall thickness and less reduction, and there is a less preparation needed for certain areas, especially the cosmetic zone. But we're going to discuss that. But I want you to bear in mind what I said here, what I put up here. We're talking about 1 millimeter wall thickness for lithium disilicate, then 1.5 millimeter. So you're saying about 1.5 millimeter lithium disilicate, 1 millimeter zirconia reduction all around, roughly. Okay. Now preparation guidelines. I want to show you some conclusions. All right. Monolithic zirconia crowns exhibit higher fracture loads than monolithic lithium disilicate crowns, of course, right? Or layered zirconia crowns and metal ceramic crowns. So the best that you can do is a monolithic zirconia. All right. Now the fracture resistance of monolithic zirconia crowns with a thickness of 1 millimeter can be equal to metal ceramic crowns. Those are the conclusions of some studies that I've read and I concluded for you guys. Doubling the monolithic zirconia core from 0.6 millimeter to 1.5 millimeter increases the fracture resistance of this restorative system threefolds. All right. So instead of 0.6, you increase it to 1.5. You're talking about triple the strength of that zirconia. Now, some conclusions of multiple studies for discussion. The reason I say it's for discussion is because I do disagree with some of them. Anyways, the fracture strength of the zirconia monolithic all ceramic crown with higher thickness increases. The higher thickness, the more fracture strength and the more resistance to fracture. Now, the fracture strength of 1.1 millimeter thickness zirconia monolithic or ceramic crown was higher than the fracture strength of 1.5 millimeter thickness lithium disilicate crown. If you have in the functional zone in the posterior, if you have a clearness of 1 millimeter, go ahead and do it with zirconia. All right, 1.1 is even stronger than 1.5 lithium disilicate. So if you only prepare 1 millimeter or 1.1 millimeter and ask for a monolithic zirconia, it's even stronger than preparing 1.5 millimeter initially, of course, preparing 1.5 millimeter for lithium disilicates. In other words, zirconia is stronger than lithium disilicates in this study. Now, the fracture strength of 0.5 millimeter thickness zirconia monolithic or ceramic crowns exceeded maximum occlusal forces. I put this study to go against it, not to use it as a proof. All right, fracture strength of 0.5 millimeter thickness zirconia monolithic or ceramic crowns exceeded maximum occlusal forces. I don't know what kind of maximum occlusal forces they're talking about, but 0.5 millimeter thickness of zirconia is weak, and we will look at that and we will discuss that into further details in this part of the lecture, in this video. All right, but I put it up because people are gonna say, oh, but there's studies that say 0.5 millimeter thickness is enough. We will see that in details from different studies and compare it to each other. Now, monolithic zirconia crowns present higher fracture strength than bi-layer veneered zirconia after artificial aging and surface finishing. Now, surface finishing does not affect their fracture strength. However, monolithic zirconia crowns present higher fracture strength than bi-layered veneered zirconia. All right. There is no difference in strength between crowns made of high translucent or low translucent zirconia. This is a conclusion of a study too, and I put it to go against it. Of course, there is a big difference between the strength in high translucent or low translucent zirconia. They probably run this study on a specimen that has different translucencies but close to each other, like in the same range, like in the 4 deuterium stabilized zirconia range or in the 5 deuterium stabilized zirconia range. And then they came up with that there is no difference, for example, between two different products in the same range but with a little bit different translucency, because it doesn't make any sense. For you to gain translucency, you lose strength, and there is it's been discussed in details in the previous videos if you want to go back to it. But there is four factors that affect translucency, and there is factors that affect strength, and we talked about all of that, and we talked about the factor that affects low temperature degradation as well. All right. Now, at equal thickness, the strength of zirconia crowns was significantly greater than that of lithium disilicate glass ceramics. Of course, if you have to choose, and you have a choice of making it a monolithic zirconia, when it comes to initial strength, zirconia is stronger in the same thickness. If you're talking about the same thickness, it's stronger than lithium disilicates. Initially, as dental lab material, regardless of the strength that lithium disilicate gains after cementation, if it's chemically etched, of course it gains strength. So, in other words, we're talking about initially about the material itself. Now, while they have superior aesthetics, glass ceramics exhibit lower strength but higher chip fracture resistance relative to porcelain veneered zirconia. Of course, because it's monolithic, all right? Glass ceramics exhibit lower strength but higher chip fracture resistance, all right, relative to porcelain veneered zirconia. Translucent and shaded experimental zirconia yield superior wear behavior and low antagonist wear compared to lithium disilicates. All right, so zirconia were opposing dentition less than lithium disilicate. Okay. So translucent and shaded experimental zirconia yield superior wear behavior and lower antagonist wear compared to lithium disilicate. Okay, I see now. Okay. So it has lower wear compared to lithium disilicates. So the wear of opposing for a zirconia is lower than the wear of opposing of a lithium disilicate. All right. A trend to higher ceramic and antagonist wear was shown after grinding and glazing. All right, so there is more wear when you grind and then glaze. So there is less wear if you polish after grinding. So you did your selective grinding, okay? You're better off polishing. You will eliminate the wear of the opposing when you polish, better than reglazing. All right. You know, as a lab technician, when you get something back for a reglaze, please make sure that you refine that surface. Mostly when a dentist performs selective grinding, you will see that the tools that the dentist and the speed that the dentist use with the high speed, you know, you see that the reduction, the occlusal adjustment is really rough. Okay, so make sure that you before polishing, prior to polishing or glazing, make sure that you smooth it very well and then you glaze it. Alright, so that's probably why. But in the other hand, we established that polishing is the best when it comes to effect on the opposing, the wear of opposing. Polishing is your best bet after selective grinding or after occlusal reduction or occlusal grinding. And then second ranks glazing, and then third and the worst is not doing anything about it. Just grind and, you know, and not do anything about it. It will wear the opposing very badly. All right. Now the last one, fracture loads for posterior lithium disilicate crowns with 0.5 millimeter wall thickness were too low to guarantee a low complication rate. So 0.5 millimeters for lithium disilicate showed a failure. Okay. Now, whereas all crowns with 1 millimeter and 1.5 millimeter wall thickness showed appropriate fracture resistance in lithium disilicates as well. So once you increase it to 1 and 1.5 wall thickness, you're doing good. Just like the Spear Education recommendation, they said 1 millimeter wall thickness of lithium disilicate. So here it says 1 millimeter to 1.5 millimeter wall thickness of lithium disilicates in the posterior area showed a good fracture resistance. Okay. Now differences between crowns with 1 millimeter and crowns with 1.5 millimeter wall thickness were not significant. So 1 millimeter wall thickness for lithium disilicate in the posterior area is good enough, they're trying to say in this in the conclusion of this study. Okay. Now we're going to be looking at many companies' recommendations. Look, these are anterior crowns, 1 to 1.5 labial reduction, 1 millimeter deep chamfer margin, veneers, 3 to 0.7 millimeters chamfer margin, whatever. IPS Emax posterior crown, look, they're still talking about this is Emax. In other words, lithium disilicate, okay, posterior. Talking about 1.5 axial, okay, wall, which is wall thickness, 1.5 millimeter. And we established that 1 is acceptable, right? 1.5 millimeter occlusal reduction, 1 millimeter deep chamfer reduction. Now you come to Katana posterior crown. Katana is Noritake, and it doesn't have lithium disilicate, it only has zirconia. So everything that you see here that says Katana, it's a zirconia, okay? Zirconia, 0.5 occlusal, 1 millimeter wall thickness, and then 0.5 millimeter deep chamfer margin. Proxizor, you're talking about 1 millimeter wall thickness, 0.5 millimeter occlusally, 0.5 millimeter chamfer margin. All right, and then inlays and onlays, and Maryland bridges. But look, know that Katana and Proxizor in the chart are both of solid posterior deuterium stabilized zirconium oxide. Okay, deuterium stabilized zirconium, like the solid zirconia, the strong zirconia, not the 4 deuterium stabilized or 5 deuterium stabilized. You're talking about the 3 deuterium stabilized, like tetragonal zirconia stabilized with 3 molecules of yttrium oxide, okay, that we discussed before in the previous videos. Now this is Noritake. Same thing, you're talking about zirconia. Zirconia here in this zone, Kurari Noritake, in this zone you're talking about 1 millimeters wall thickness as well, and 1 millimeter by the gums, by the margin. 1.5 millimeter occlusal cusp, all right, the cusp tip. Here same thing, 1.5, 1 millimeter. No matter how you look at it, anterior or posterior, okay, whether it's a framework, that's what I want to show here, whether it's a framework or it's a full contour zirconia, it doesn't change. 1 millimeter is the least you can go with posterior zirconia, whether a core or a full contour, and 1 millimeter, same thing here, is the least that you can go with an anterior, whether it's a full contour or a framework. This is from Noritake, Kurari. This is their recommendation, okay? Because you get people telling you that, oh, if you make a shell zirconia crown, like a 0.5 all around, what do you think of that? So that's why I'm showing all of this spear education recommendation as well as company recommendations, and we will show much more than that. Okay, 1 millimeter axial wall reduction for full contour zirconia is highly recommended, just as it is for a core material or a framework when there's a bridge. All right. Now let's take a deep look at this. Same thing, Noritake Kurari. They have these products: UTML ultra translucent multilayer zirconia, STML super translucent multilayer zirconia. The first one, UTML, is 557 megapascal. The STML is 784 megapascal. Then there is a medium, there is high translucent and multilayer and high translucent, high flexural strength zirconia up to 1150 megapascal. And I want you to notice certain things. If it's in your area that you don't use these blocks that much, these zirconia blocks, I want you to notice a few things. First of all, look at the naming: multi-layered and high translucent, high flexural strength zirconia. When you hear high translucent or multi-layered or high translucent, you would think that this is a very high translucent zirconia and that it has a reduced mechanical properties, because higher translucency pretty much means lower strength. But here it says flexural strength zirconia is 1150, almost 1200 megapascal of strength. So if this is translucent zirconia, then what is this? A super translucent multilayer zirconia, and then an ultra translucent multilayer zirconia. A person would wonder, what are they gonna name the next product? Ultra super supreme translucent multilayer whatever zirconia. I mean, you're naming everything high translucent pretty much, whether you say super translucent, ultra translucent, or high translucent. It's all translucent material you're saying. But looking at the flexural strength, I can tell that this is for posteriors, the 1150, the ML or HT. It's 1200 megapascal of strength, unless they managed to have a high translucent zirconia with that much of strength, and I don't know of any company that have managed to do so far. Okay, so here we have to put them into different diagrams. One for the real translucent, the translucent that we understand, the real translucent zirconia, which is UTML and STML, which is ultra translucent multilayer and super translucent multilayer. Those are translucent zirconia that we know. Look at the recommendations here. First of all, you will see a veneer and you will wonder, can we make veneer out of zirconia? We will answer that later. Now here's anterior crowns. We're talking about 0.8 millimeter all around as an anterior crown, and 0.4 millimeter as a veneer. Okay? Zirconia. This is all zirconia blocks. They don't have lithium disilicates. Kurari, Noritake don't have lithium disilicates. We're only talking about milled zirconia prosthesis. Okay? So this is a milled veneer and this is a milled anterior crowns. A milled veneer where there is no occlusal forces and nothing is there, you can go as low as 0.4. Okay? Here as low as 0.8 for a crown, and then 1 millimeter all around when you go to posterior crown. You see, nothing less than 1 millimeter. Not by a recommendation of Spears Education, not by the recommendation of any company. 1 millimeter zirconia in the posterior. This is what's going to give you the strength. All right, only and only. It's not our study at this point of the time. Now, when you go to HT or ML, which is the high flexural strength zirconia, okay? High flexural strength zirconia, we're still talking about the same parameters. Here, you're talking about 0.4 millimeter veneer. You can't go less than 0.4 millimeter of a veneer, okay? When it comes to zirconia veneers, and we're going to discuss zirconia veneers in details. And then here you went down to 0.4 millimeters. Why? Because it's high strength. It's less translucent, regardless of the name. It's less translucent. So here you have 0.4 millimeters of this crown anteriorly, anterior crown. Once you want to go back to posterior, this is what gives you 0.5 millimeter of posterior crown, and I am against it, period. I don't think that you should go less than 1 millimeter in the posterior region. Now over here they tell you yes, you can go 0.5 millimeters all around for a posterior crown, but using the high flexural strength zirconia. You're only talking about HT or ML from Katana, or you're talking about Proxizor that can give you the 0.5 millimeter, and I think that you are on the edge. You're risking too much by going 0.5 millimeter. Now Proxizor, we know that it's very hard, it's very strong, and you know they say that you can use 0.5 millimeter in the posterior area. I just mark my objection on that. I think it's too thin, and even in the manufacturing process, I do not like to mill anything less than 0.6, 0.7 millimeters on my CAD cam, even though it's a 5-axis CAD cam and it's stable and there isn't much vibration in the machine. But whatever, I just find that 0.4 or 0.5 millimeter shell is really susceptible to cracks and micro cracks, and it can fracture. Now I understand the approach of being you don't want to prep too much from the tooth, and you want to preserve vital tissues and all kind of stuff, vital structure of the tooth, and I know the conservative approach of it. But in the other hand, I think that according to what the company says, if you want to go and push it to this limit, 0.5 millimeters of zirconia in the posterior region, then you have to make sure that your lab is using the high strength. Your lab is not using HT plus, for example, high translucent plus, or ultra translucent multi-layer, or super translucent. You have to make sure that the lab is using the core material, which is the dull material, the material that doesn't look good, okay? Even after staining and after everything, because it's just a dull 3-deuterium stabilized tetragonal zirconia material. It's really dull and doesn't look good. So if you want to use that, you probably can go and consider just a core shell type of prosthesis. It's up to you, but I rarely find this justified practice, honestly. But it's just my opinion. You can go ahead and do it. Which type of zirconia is the lab using for your case? This is very important to know. Where does your prosthesis fall? Does it fall in the 1 millimeter area, or does it fall in the 0.5 millimeter area, or does it fall, or where does it fall, based on knowing what does your lab even know the kind of material? Does the lab use high translucent material posterior and anterior? Does the lab differentiate from when should I use high translucent, when should I use, for example, in this chart, when should I use UTML or STML or ML or HT? Difference between them and the uses, difference in uses in aesthetic zone versus functional posterior zone, okay? Now we come back to this. Is there etchable zirconia veneers? Are they etchable? Are they translucent? Are they strong? We will answer all of that, okay? Now, this is the base study that most people rely on. This study and some other study that I will show next, okay? when they talk about etchable zirconia. Improved resin zirconia bonding by room temperature hydrofluoric acid etching. Now, this is quoting and conclusions from this long study. It says, application time is more critical than the concentration, because many people try to use 90%, 100% concentrated hydrofluoric acid and see the difference. But really, the difference is in the application time rather than it being in the concentration of the acid. Okay, thereby creating a mechanical. Now, what happened is it did cause a surface roughening and thereby creating a mechanical interlock after polymerization of the resin. So in other words, surface roughening, the resin or the resin cement goes inside and does an interlock, mechanical interlock inside of these let's say the surface becomes porous. The surface becomes, there is roughening in the surface. So it acts as an interlocks, where the cement goes in and locks itself. So it gives you a better interfacial cement bond between the abutment, the tooth, and the zirconia. This is by etching the zirconia for 30 minutes. All right, you etch the zirconia for 30 minutes. With 30% concentration hydrofluoric acid. I will show a couple of companies that came up with a way of etching. All right, but let's understand what does it do. Now, the mechanical properties or strength of zirconia after hydrofluoric etching should be further evaluated. Absolutely. This is a new way of doing things, as to speak, and we want to see what kind of mechanical properties, especially that you're talking about surface roughening again. And surface roughening in zirconia, in the back of our minds, has an issue, because you're talking about, even LTD, low temperature degradation. The problem of low temperature degradation is surface roughness and then micro cracks. Okay, there is a toughening, there is a transformational toughening, but that doesn't mean that there is no cracks. There is surface uplifts and it will cause micro cracks, and yes, there is a stopping mechanism and hindering mechanism of the crack propagation, but there is cracks on the surface. Now you're doing the same thing. There is surface roughening inside of that core, inside and outside, because they submerge the whole thing. But inside of the core, or inside of that monolithic crown, there is now a rough surface that you created by etching the inside. I understand that the cement supposedly goes inside and interlocks and everything, but would this ignite, or would this start a micro crack from inside? Would this affect the mechanical properties and the strength of zirconia? Is there a study that shows that after etching initially, the mechanical properties are the same? There is actually a study that I will show in this video, but it's initially. I want to know after a while. We want to see the success rate of the etched zirconia. This is exactly what I want to say. We want to see the success rate of etched zirconia after 5 years, for example, after 10 years, and it's a new technique, so we don't have that longevity of studies to show anything about the etched zirconia, but this is how they etch it. Long-term clinical investigations are necessary to ensure the clinical efficiency of hydrofluoric etching of zirconia for improved resin zirconia bonding. Okay, now this is a study to effects of acid treatment with ultrasonic on resin zirconia bond strength. There is a couple of things that I want to quote from this study. To promote micromechanical interlocking, many surface roughening methods for zirconia were developed. Right? Now, what's the year of this study? I think this was 2015 or 17. I'm not sure. I will look for it. All right. Now, due to its resistance to conventional etching techniques, alternative surface etching techniques of zirconia coping has been introduced to increase the surface roughness. Okay, found that hot acid etching increased the bond. It's not just a cold acid; it's hot acid inside of ultrasonic. All right, It increased the bond strength between zirconia and resin. Mechanical property of zirconia were not affected. All right. They found out that it's in this study that it was not affected, which in turn was due to its low handling temperature. All right, now this is initial. This is initial. I want to see this after 5 years or 10 years. What's the effect of it? Is there any difference? Like if we take, you know, how you do it. You take a sample of 100 crowns, 50 of them are etched, and 50 aren't, and you cement them, and you see the success rate after 5 years or 10 years. We don't have such a study for a technique yet. It's a new technique. All right, created excellent three-dimensional network. Zirconia could be dissolved effectively in acid with ultrasonic. Now shear bond strength of resin cement on etched or non-etched zirconia. Now the purpose of this study is to investigate the shear bond strength of resin cements on etched or non-etched zirconia oxide blocks. Okay, we understand that. But the thing is, like I said, you are doing something that's new with etching zirconia to promote the cementation. Does that affect the physical properties on the long run? You know, they obviously in this study proved that zirconia were not affected. That mechanical properties of zirconia were not affected, which in turn was due to low handling temperatures. But we want to see that on the long run and see the effect of it on the long run. But yes, people started etching zirconia, and I will show you. This is the company. This is made in Korea, and it's approved by FDA. It's called Zircos E, and it's an etching zirconia kit. You see, this is the box. It's like sandblast box, but it's sealed from all around. And then there is the etching, the zirconia etching liquids that you put inside of here. You leave it for 30 minutes, and then you got yourself an etched zirconia. You can go ahead and use it. All right. And this is just a promotion for this new technique. If you want to take, you know, the course and see how you can etch it with Zircos E for the ultimate etching experience for this zirconia. But I've showed you the studies, and I've showed you what people rely on when they talk about surface roughening or etching of zirconia, the internal aspect and the external aspect of it, and that it will improve the bond with the ceramics from the outer part of the coping of the zirconia. You're talking about interface of zirconia veneered or zirconia porcelain bond interface, as well as the inside, which is the resin cement, the resin interlock that is established with the inner aspect of the core, since it's been etched and surface roughened. Okay, so that's the issue of etching zirconia. Now we move on to 3D printing zirconia. I want to finish really with this before I stop with the video. You know, any additive manufacturing or AM, any additive manufacturing is more accurate than any milling or reduction manufacturing, pretty much. So 3D printing ceramics, there is machines and studies about it. Application go beyond the classical crowns or bridges, and also the use of printer components in applications such as mandibular cages, craniomaxillofacial surgery, or dental implants. I will show all of that. Okay, applications where bone regeneration needs to be induced, that too. Okay, now this is just the differences in the printers. Ceramic 3D printing technology type, the technology type and how was it used and everything. With slurry based, powder based, bulk solid based, that doesn't concern us right now. Additive manufacturing is also known as 3D printing. Okay, additive manufacturing technology. There's this Lithos company. It's a leading company in this field. All right, and I think I put a post about it towards the end of this lecture, if I'm not mistaken. They're printing zirconium oxide, aluminum oxide, silicon oxide, silicon nitride, and other things. This is their machine. It's very expensive. It's around $300,000. But it's high in performance, and I think in dental we have smaller ones, cheaper ones that can print zirconia these days. You can print all of the above. Mandibular cage made of zirconia. Parts consist of both ceramic particles and an organic photopolymer network. Okay, those are dental implants, and those are printed TCP scaffold with customized outer shape and interconnected macroporous as used in a mandibular cage. What concerns me right now is let's first finish up with 3D dimensions and then show you the crowns that it prints. Now, using LCM, it is possible to obtain high dense 99.8% relative density of zirconia structure. All right, and then ultra thin occlusal veneers. That's our core product. Ultra thin occlusal veneers. Okay, produced like crowns. Occlusal veneers produced via the LCM process are compared to milled zirconia and to pressed lithium disilicate reconstructions in strength, they mean. All right, now the high accuracy and thus high internal adaptation achievable, of course, because it's like we said, it's additive manufacturing, so there's a better adaptation. Adaptation achievable through additive manufacturing is better than milling. All right. Now this is how they look. I don't know what machine this was produced from, or what machine produces this. There's many machines in the market now, cheaper than the lithos, of course, and this is the way they print zirconia. And there's one more thing. They say that it comes with, it's thermally etched. You don't need to etch it. Like we said, the chemical etching or the mechanical etching. You're talking about thermally etched zirconia. And I don't know what thermally etched zirconia means. I don't know how you can etch it thermally. But this is comes with the printing of the zirconia. Like printed zirconia are thermally etched. I have no idea what this means, but let's wait and see what kind of, if it's etched, you know, and without using hydrofluoric acid, without using anything, you just cement it, that would be great. Now there's injectable zirconia. Injectable zirconia really, we're still far away from achieving anything pretty much. This dispersion is subsequently deposited using a syringe-based three-dimensional printing equipment while being cured using a power lead source. This is a printed sample using the 30% volume zirconia dispersion. It pretty much just it's like you dispense this zirconia and then you light cure it, something like that. Okay, now there is things to say about this. Using the solution mixing principles showed the most desirable properties. No problem. A better matched UV source with a higher irradiance is thus desirable because they figured that there is an issue in the light curing. It should be evenly distributed on the sample in a better way. A large shrinkage was experienced during sintering caused by an insufficient amount of ceramic particles in the dispersion. Like I said, we are far away from achieving anything with injectable zirconia. And when you want to think about it as, say that you want to do a full mouth lower zirconia, for example, injectable, you need a mold. You need some molding technique to give you an outer limit and an inner limit for that bridge, and then holes to inject, and then make sure there is no bubble trapping and all kind of stuff. So it's not really clear when we're gonna get a breakthrough in the injectable zirconia, and still under study, but I want to put it up anyway just to show you the different ways of handling zirconia. Now, preparation guidelines. This is 40 minutes. I have to stop. From Kurari, it's just contraindications. All right, sharp incisal, parallel axis, grooves, height differences, rough margin, undercuts, knife edge, deep chamfer, J margin for ski jump. Okay, so these are contraindications in the preparation for Kurari, which is zircon block, whether monolithic or layered. Cementation advices. This is a clinic side issue, and I just put it up because many of the people who attend my live lectures are dentists. So if there's a question about cementation, I'm not very familiar with the cementation because I'm a dental technician, so I put these up just for them to take a screenshot of it or whatever. Same thing here, okay? Or ceramic cementation guidelines. Now we discussed what would be considered as a sufficient wall thickness reduction for a posterior monolithic zirconia or glass ceramics. We said 1 millimeters at least if you want to be safe. All right, the least reduction you give, the more chance you take. Is there a maximum thickness recommendation for a monolithic? Nothing that I know of. No, there isn't a maximum thickness recommendation. Preparation contraindications, we talked about this. I will stop right here and then just show a couple of shade matching techniques and proceed to monolayer technique that I do. Thank you for watching.